Okay, welcome, and we're going to start our discussion with graph theory. And so we're going to go through this textbook, and I'm going to highlight some things, and we'll go through some examples as well. Let's pull up the whiteboard. Okay, so here we go. Um, so in the modern world, planning efficient routes is essential for business and industry, with applications as varied as product distribution, laying new fiber optic lines for broadband internet, and suggesting new friends within social network websites like Facebook. Okay, this field of mathematics started nearly 300 years ago as a look into a mathematical puzzle that we're going to talk about in a little bit. The field has exploded in importance in the last century, both because of the growing complexity of business in a global economy and because of the computational power that computers have provided us. Okay, so we're going to look at this example. So we're going to look at basic concepts and definitions. And so it says here is a portion of a housing development from Missoula, Montana. As part of our job, the development's lawn inspector has to walk down every street in the development, making sure homeowners' landscaping conforms to the community requirements. Okay, so the idea here is she probably just wants to walk down, and she wants to minimize the amount of walking that she's doing, right? So being able to walk down, let's say, one street only once, to get around to looking at each house, that is the question, right? And so here we have all these different streets, right? So we have a street that goes down this way and then down this way. We have this street here. Oh, we also have this street here that goes that way. So we're trying to find, what we want to do is we want to find a route around the neighborhood that goes down each street, but only once, right? So finding that route, so that way you walk the minimum amount of distance, right? Okay, so that's what part of the discussion is going to be about. Now, naturally, like I was saying, she wants to minimize the amount of walking she has to do. Is it possible for her to walk down every street in the development without having to do any backtracking? While you might be able to answer that question just by looking at the picture for a while, it would be ideal to be able to answer the question for any picture regardless of its complexity. To do that, we first need to simplify the picture into a form that is easier to work with. We can do that by drawing a simple line for each street. Where the streets intersect, we will place a dot. Okay, so you can see here on the left is a graph of sorts, right? And then we can also look at just this diagram, this graph here. And so this type of simplified picture is what we're going to call a graph. Okay, so the definition of a graph's vertices and edges. So here we go with our first definitions, right? So a graph consists of a set of dots or circles called vertices and a set of edges connecting pairs of vertices. So this here, right? So if we look at this here, this is what we're going to call an edge, where this dot here labeled K is going to be a vertex. Okay, so where the lines intersect at these dots is a vertex. Okay, and so this whole thing we're going to call a graph. Now, while we drew our original graph to correspond with the picture we had. There's nothing particularly important about the layout when we analyze a graph. Both of the graphs below, so this one here, okay, and this one on the right, both of the graphs below are equivalent to the one drawn above, since they show the same edge connections between the same vertices as the original graph. Okay. Now, as you probably already know, we're not using the term graph the same way that we normally would in an algebra class. Okay, where we describe the graph of a mathematical function, right? Okay, so now example 2. So now here we look at a classical problem. So it says back in the 18th century in the Prussian city of Königsberg, a river ran through the city and 7 bridges crossed the forks of the river. The river and the bridges are highlighted in the picture to the right. As a weekend amusement, townfolk would see if they could find a route that would take them across every bridge once and return them to where they started. Now, Leonhard Euler, one of the most prolific mathematicians ever, looked at this problem in 1735, laying the foundation of what we're going to call graph theory as a field of mathematics. Okay. To analyze the problem, Euler introduced edges representing the bridges. Okay, so if you look at this graph down here, okay, so these lines connecting the north bank to the island are edges, as well as the line connecting north bank to east bank. Okay, so those are the edges. But we could have done this a little differently. So since each size of each of the landmass is not relevant to the question of the bridge crossings, each can be shrunk to a vertex representing the location. So we can rewrite the graph or redraw the graph like this. Okay. Now notice that in this graph, there are 2 edges connecting the north bank and island, corresponding to the 2 bridges in the original drawing. So if you look at the original drawing here, right here. Okay, so these bridges up here in green are what we're representing. We're representing them as edges in the graph below. Now, depending upon the interpretation of edges and vertices appropriate to a scenario, it is entirely possible and reasonable to have more than one edge connecting 2 vertices. Okay. While we haven't answered the actual question yet of whether or not there is a route which crosses every bridge once and returns to the starting location, the graph provides the foundation for exploring this question. Okay, and so we'll come back to this. So now here are some definitions. Okay, so we're going to talk about definitions, and then we'll leave it at this. So definition 1 is a vertex. Okay. So a vertex is a dot or small circle in the graph that could represent an intersection of streets, a landmass, or a general location like work or school. Vertices are often connected by edges. Notice that vertices only occur when a dot is explicitly placed, not whenever two edges cross. Imagine a freeway overpass. The freeway and side street cross, but it is not possible to change from the side street to the freeway at that point. So there's no intersection and no vertex that we would place. Okay, now edges. Okay, so the definition edge goes like this. Edges connect pairs of vertices. An edge can represent a physical connection between locations, like a street, or that a route connecting the two locations exists, like direct airline flights. Okay. We often will describe an edge as a combination of letters like A, B that are next to each other, right? That are sequenced, right? So A, B, where A and B are the endpoints. Okay. Now, the next definition is adjacency. We say that two vertices A and B are adjacent if there is an edge connecting them. Okay, so two edges, E and F, we are called adjacent if they have a common endpoint. In other words, if they have a common vertex. Okay, the next definition is a loop. Now, in some cases, now again, you may have a special type of edge called a loop. So a loop is a special type of edge that connects a vertex to itself. Loops are not used much when we talk about street network graphs. Okay, you won't see, but you'll see them in other types of graphs that we'll discuss later. Okay, and then also degree of a vertex. So when we talk about the degree of a vertex, the degree is the number of edges meeting at the vertex. So if you look at the bottom pictures, you can easily see why, what the degrees are and why. Okay, it is possible for a vertex to have a degree of 0 or larger. Okay, so degree 0 means that there's no edges connecting it. Degree 1 means you have one edge. Degree 2, there are two edges connected to the vertex, and so on and so forth. Okay, so that's where we'll stop, and we'll pick it up next time.